In this video, I'm going to go through 3 different proof by contradiction questions. I'm going to show you a 2-step method which tends to help with most questions, and I'm going to show you one unique question, which is this first one actually, that's a little bit outside of the box. So with proof by contradiction, you want to start by making an assumption that proves the opposite of the statement is true. So here it says the sum of rational and irrational is irrational. We're going to assume the opposite. We're going to assume that the sum of rational and irrational is actually just rational. So let's do that to start with. Assume for a contradiction the sum of a rational and irrational number is rational. Okay, where do we go from there? Well, now we have to somehow disprove this assumption, because if we disprove this, then that means that the opposite of this statement, which is the original statement, is correct. So how do we disprove this? Well, let's represent this algebraically. A rational number can be written in the form a over b, where a and b are integers, in the simplest form. That's just a fancy way of saying that all rational numbers, they can be represented by fractions where the top and bottom of the fractions are whole numbers, like 3 over 5, 4 over 7, 9 over 11. I'm sorry, I shouldn't have said those numbers. 9 over 13, but yeah, you guys get the idea. A and B are integers in the simplest form. How do we represent an irrational number then? Okay, so we're adding this to an irrational number. Unfortunately, there's no fancy way of representing an irrational number. Let's just represent it with a singular letter, where C is irrational. And that's equal to another rational number. So let's represent that as D over E, where D and E, once again, are integers in simplest form. So I'm just going to copy and paste this from here because it takes ages for me to write for some reason. Just spare me one moment. Integers in the simplest form. Okay. How do we now disprove this here? Well, if we think about it, if we subtract a over b from both sides, we get that c is equal to d over e minus a over b. So according to this assumption, an irrational is equal to a rational take away another rational. If we manage to somehow combine these two subtractions into one singular fraction and show that the top and bottom of the fractions are both whole numbers, then that shows that, well, the right hand side is actually just rational, meaning this here is false. It's not irrational. So let's do that. With subtraction fractions, you know that you cross multiply. D times, so let's do that here. D times B is DB minus A times E is AE, all over the multiplication of the denominators, EB, is all equal to C. So D times B is an integer multiplied by another integer. So I'm just going to write here int for integer, and we're taking away from it A times E. Again, A is an integer and E is an integer. So this, you're taking away an integer from another integer, and you're dividing all of that by E multiplied by B, both of which again are integers. Let's think about this. Any integer take away an integer is always going to be an integer. I've said the word integer quite a few times. It only means it's just whole numbers, whether it's 0, positive, or negative. If you do 3 take away 1 over something like 7, you'll see that it will again give you a rational number. And that disproves the assumption, because our assumption previously was that C is irrational, whereas we've just proved that C is just rational. So let's say that conclusively. We say since the subtraction of two rationals is rational, C must be rational. The fact that this disproves the assumption, and then you just want to make another statement like the original statement is true. Perfect. Let's now move on to this next part of the question. Use proof by contradiction to show there exists no integers x and y for which this equation is true. Well, let's think about it. Well, once again, we're going to start by assuming the opposite. So we're going to assume there exists integers x and y such that 6x plus y, 9y, sorry, is equal to 1. Now, if we assume this, One way to disprove an assumption, or two ways that tend to always help in these exams, is either by factorizing or by squaring both sides of the expression. And you choose which one to do based on the question. So here, the left hand side, what we can notice is that 3 is a factor of both 6x and 9y, so we can factor out 3. So I think this is the best way to disprove the assumption. Let's go about doing it. So if we factor out 3, 2x plus 3y equals 1. Then we can divide both sides by 3 to get 2x plus 3y equals a third. So where does this take us? How can we show that this statement here is false? Because we want to disprove the assumption. Well, let's think about it. If x is an integer like we're saying, then 2x would also be an integer. Any whole number multiplied by 2 will just be another whole number. Same with y. If y is a whole number, then 3 multiplied by y will also be a whole number. Whenever you add together two integers, 9 plus 10, 11 plus 2, whatever two integers you add, it will always give you an integer. Whereas the right hand side of this expression, a third, is not an integer. So that's what disproves the assumption. Let's put that in text format. You can say this disproves the assumption. So the original statement, or if you want to be fancy, you can say the original conjecture is correct. Let's now move on to this third one, and this is where squaring helps. I'm sure you've seen this in class, because this is the one that comes up most commonly in exams. So we're going to start by assuming the opposite one more time. We're going to assume that the square root of 3 is rational. Once again, how do we represent a rational number? We did it previously actually. We say it can be equal to a over b, where a and b are integers in the simplest form. You might be wondering why do I keep saying simplest form and what's meant by that. Well, I'm just going to finish writing this out and then I'll explain. Well, if it's 11 over 22, a over b, that's the same as 1 over 2. So you'd much rather write it as 1 over 2, in which case it would be in its simplest form. That's what's meant by that. And actually, we're going to prove that they're not in the simplest form. That's what we're going to use to disprove the assumption. So how do we go about doing that? I mentioned you either want to factorize or square both sides, depending on the question, to disprove the assumption. Here it makes sense to square. You can't really factorize anything here. I'm actually going to change the thickness of the pen. Okay. When squaring both sides, root 3 all squared gets rid of the square root, so you're left with 3. A over b all squared is a squared over b squared. And you can multiply both sides by b squared to get a squared equals 3b squared. Now, why is this important? That means that a squared is always a multiple of 3. So you can make a statement here. Since a squared is a multiple of 3, a is a multiple of 3. This is actually a fact, and it applies to all multiples. If a squared is a multiple of 10, a would be a multiple of 10. So it applies for any number, like I said. So a is also a multiple of 3. Now that we know a is a multiple of 3, we can let a equal something like 3k, where k is a whole number, where k is an integer. Okay, why do we do that? Well, once you've done that, you can square both sides and say that a squared is equal to 9k squared. So you can say 9k squared is equal to 3b squared. You can divide both sides by 3 to get 3k squared equals b squared. And then you also get that b squared is a multiple of 3. So once again, you can make another conclusive statement. Since b squared is a multiple of 3, you can say b is also a multiple of 3. What we've done just now, we've shown that a and b are both multiples of 3. But what did we say before? We said that a and b are in their simplest form. Well, they can't be in their simplest form if they're both multiples of 3, because then they'd cancel each other out with a factor of 3. So let's try that out. Actually, I'm going to do it here just so you can see the rest of the working out while I do it. We can say, since a and b are multiples of 3, they are not in their simplest form. You can say that this disproves the assumption, and so once again the original conjecture holds true. Conjecture holds true. Yeah, great. That's everything for this question. Hopefully that one made sense to you guys. Be sure to like the video if it helped and subscribe. If you'd like me to make another video about proof by contradiction, or if you have any specific question you'd like me to go through, just type it up in the comments and I'll have a look. Bye.